In this fourth and last video on the iteration method, we are going to have a look at a little bit more details about it. So keep in mind that this method is useful for solving equation of this kind, where f of x is equal to x. So to do this graphically, to interpret this graphically, we need the graph of the function f in blue here, and we need the line y is equal to x. And as we've seen in the previous videos, graphically, the process of applying the function f repeatedly from a starting value here leads us to this answer. Geometrically, it's because you basically bounce from the curve to the line with the equation y is equal to x. And you see, if you use your calculator to do this, that your values are going to get closer and closer. One thing that can happen, especially when the graph here goes down at the point of intersection, is that if you start from x, you will get on the curve here, bounce down here on the curve again, go on y equals x, and go on the curve, etc., etc. So here, you'll be spiraling to the answer, meaning that you will get values of x that alternate, that are smaller than and then greater than the expected answer. And you keep on getting approximation that are smaller and greater than your final answer. My second comment about the iteration method links to the cases where this method is going to work and the cases where, unfortunately, this method is not going to work. At GCSE level, you will be given the function and you'll be given the starting value, so you don't have to worry about this. The method should nicely apply. But at A level, you might have to actually deal with some situation where it doesn't work. For this function, for example, you see that if you start from this value of x, you can get f of x with the y coordinate of this point, so it's there. And then you apply f again, so you get this one, and then you apply f again, so you get this value, and you apply f again like this, and you see that basically you started from here, and you're just moving away from the solution would be there. This relates to the fact that the gradient of this curve here is greater than 1. And it would be the same if this gradient was less than -1. So you don't want the curve to be too steep where it meets the line y is equal to x. Otherwise, the value will just diverge from the solution you are expecting to find. So how can we deal with this kind of situation? Well, the answer to that is actually pretty simple. And we are just going to use the reflection of this graph into the line y is equal to x. And if we add in blue the graph of y is equal to f of x, what we need to plot in green is the graph of y is equal to the inverse function of f. This graph will be the reflection of the blue one in the line y is equal to x. And here, the gradient on the green line will be less than 1 if this one was more than 1. And you can see that now if you try and plot the path of, the iteration, we are going to get something that goes like this, and that will converge to our solution nicely. Another option would be to rearrange the equation you're trying to solve differently. For example, if you're trying to solve x cubed minus 4x plus 2 is equal to 0, you have to turn this equation into something of the kind x is equal to f of x. And you have different options for that. If you decide to make this x here the subject of the formula, you will end up with x cubed plus 2 over 4 is equal to x. Or if you decide to make this x here the subject of the formula, you will end up with x is equal to 2 minus 4x, and you need to take the cubic root of that. So according to the function f that you're using here or there, the graph won't have the same steepness, as it can happen that one of these two formula will lead you to a solution where the other one wouldn't. So these are the two options that you have to make this work. So either take the inverse function of the one you were using and that was diverging, or just rearrange your equation differently to get a function that will lead you to a solution. The idea in both cases is finding a function whose gradient is less than 1 in magnitude, and somewhere between 1 and -1, where it meets the line with the equation y is equal to x.